Okay, welcome to Let's Get to the Marks, going through GCSE Combined Science Trilogy Higher Tier Paper 2018. There were 6 questions. Takes an hour and 15 minutes to do one of these. We'll get through it quicker than that, I think. But what you're going to do is grab some pen, grab a paper, grab a calculator. Now, at the start of each question, press pause on the video, have a go at the question, and then unpause and watch me go through the answer with the explanation. Okay, let's get into it. Question 1. Crude oil is a mixture of hydrocarbons. The hydrocarbons in crude oil are separated into fractions by fractional distillation. Figure 1 shows a fractional distillation column. Here we got figure 1. We've got gases coming out the top. We've got crude oil coming in here. We've got bitumen at the bottom, and we've got different fractions coming out the sides. So crude oil vapor passes up the column. Complete the sentence. Choose the answer from the box below. Let's go down. Each fraction something at a different level. So why don't you pause the video and have a go? Well, each fraction, the answer, guys, is condenses. So the answer is condenses. Okay, condenses. So what does condenses mean? It means turn from a gas back to a liquid. So essentially, I'm just going to quickly whip you through an explanation of what happens in crude oil. Essentially, you're going to heat the crude oil like this. It turns into a vapor. Crude oil is a sticky black mixture that has come from the dead organisms from millions and millions of years ago when they decay under heat and pressure. Now, they vaporize at the high temperature that we heat them to at the start of the fractional distillation column or tower. They turn into gases. The different parts of the mixture move up this tower. The tower is hot at the bottom and it is cold at the top. We call this a temperature gradient. As the vapors rise up the tower, the substances that have the highest boiling point condense and become a liquid and come off here. So you have bitumen doesn't even vaporize, it just comes straight off as a liquid. But then you have things like heavy fuel oil, shipping oil, the things they use in massive container ships that carry goods from China to the UK, etc. Then we have other fractions like diesel, petrol. And finally, at the top, you have natural gases that come out at the top. They're very small molecules and they have very low boiling points, so they condense high up the tower where it's cold. Anyway, that was a little explanation. You might want to put that on a revision card because sometimes you get a 4 marker on explain how the fractional distillation works. All right, let's move on. Let's move on and I'll stop waffling. 1.2. Why do the fractions separate? So hopefully you can remember what I just said. Pause the video, have a go. Okay, the fractions separate because they have different boiling points, not melting points, because we've turned into a gas. Boiling point, condensing point, same thing. Okay, good. Let's move on. Most of the hydrocarbons in crude oil are alkanes. Figure 2 represents an alkane molecule. Name this alkane. So what you want to do here is you need to know that alkanes are called hydrocarbons. They're only made of carbon and hydrogen. What they essentially have here is a carbon chain with little hydrogens represented by these white circles coming off of them. So this alkane has 3 carbons, and then coming off of it, it has 8 hydrogens. Now, I'm not going to draw all the H's, but this means it has the formula C3H8. And they want us to name it. Well, there's a way that you can memorize this, and it is monkeys eat peanut butter. And you only have to know the first 4: methane, ethane, propane, butane. So this one we're looking at here, where the monkeys eat peanut butter, it's the peanut butter, and it's the peanut and it's propane. So the name of this alkane is propane. In fact, pro in organic chemistry is for anything which has 3 carbons in it. So propanol has 3 carbons, propene has 3 carbons, propanoic acid has 3 carbons, etc. Okay, let's move on. Okay, zinging down to question 1.4. Methane, CH4, is an alkane. What is the general formula for alkanes? So you've got to tick one box. So is the formula CnHn, CnH2n, CnH2n minus 2, CnH2n plus 2. So you need to know this off by heart. So if you don't know it, you're going to want to make a note. Now I'm going to tell you the answer and then go through the explanation. So the correct answer, guys, is CnH2n plus 2. Now, what does this mean? This means if C is 1, like it is in methane, then to find out the number of H's, you go 2 times 1 plus 2, and you get 4. Now let's look at the one we just looked at, propane. Okay, propane has 3 carbons. So what you're going to do is you're going to go, okay, C is 3. So to work out what H equals, you would go 2 times 3 plus 2, and that would give you the 8. So you can use that formula as long as you know the number of carbons, you can work out the number of hydrogens by applying this formula. So yeah, let's move on. Alkanes burn in oxygen. That's called combustion, and it releases heat. It's a really useful chemical reaction of alkanes. They make awesome fuels, things like methane, ethane, propane, butane. They're gases that you have coming out in your cooker. They're gases in your science classroom coming out the Bunsen burners. And those first 4 carbon hydrocarbons, those first 4 alkanes, are the gases you have in like camping gas and cigarette lighters and things like that. Okay, alkanes burn in oxygen. Balance the equation for methane burning. Why don't you grab a pen, grab some paper, have a go at this one, and I'll go through the explanation. Okay, here we go. Right, the first thing to do when you balance specifically burning or combustion equations, very important. You check out the hydrocarbon. The hydrocarbon is the thing made of only carbon and hydrogen, and there's 1 carbon. So we go to the carbon dioxide, and you might think, hey, do I put a 1 there? You don't need to. You don't have to use a number if it's just 1. So we can just leave it. 1 carbon means there'll be 1 carbon dioxide. Now there's 4 hydrogens. So we go over here to the water, and there's 2 hydrogens on the water. So I need to make it into 4 so that it's balanced. So if I put a big 2 here, that means 2 times, and then imagine these are in brackets. So it's like 2 times H2, which makes 4 H's, and then it's 2 times O. So you always kind of imagine the brackets. You don't need to put the brackets, but that's what you have with a big number. So what we've got to do now, we're totally balanced with the carbon and hydrogen because there's 1 carbon here and 4 hydrogens, and we've got 1 carbon here and we've got 4 hydrogens. Now the last thing to do is balance the oxygen. And in these burning equations, always balance oxygen last, or any element in an equation when it's on its own, always balance it last because it's the easiest bit to balance. So you always do that last. So we're going to go 2 times O. There's a total of 2 oxygens over here, and there's CO2. There's another 2 here. So we have 4 oxygens on this side. And so in order to balance this, what do I have to put in front of O2? I just put a 2 there, and that's going to get you the mark because now it's totally balanced. So always start by checking the carbon and hydrogen there, and then changing the number of carbon dioxide or water based on that, and then finally balance the oxygen with however many you've got on that side. Right, let's move on. Moving on down, moving on down. Okay, 1.6, ethene is an alkene. Notice there's a difference in spelling between alkanes and alkenes. Alkenes have a little E instead of an A there. Which reagent is used to test for alkenes? Tick 1 box, 1 mark, pause, have a go. Okay, I'm going to go through the answer. Anhydrous copper sulfate. Right, I'm going to explain what each one of these tests for. So this tests for water. This will tell you that you have water. It's a white powder and it will go blue with water. Bromine water. This is our correct answer. Bromine water is orange, and you need to know this, so get it on a revision card if you don't know it. The test for alkenes is bromine water. It goes orange to colorless, and you need to know that if you don't know it already. Right, damp litmus paper. We use damp litmus paper to test for ammonia, which is a gas, NH3, and then lime water we use to test for carbon dioxide, and it goes cloudy in the presence of carbon dioxide gas. Right, let's move on. You need to know all those tests, guys, so if you don't know them, put them on revision card. Best way to learn those kind of things. Okay, table 1 shows data from a life cycle assessment known as an LCA for the disposal of 10,000 biodegradable plastic bags. Here's table 1. Mass of carbon dioxide produced in kilograms, mass of solid residue in kilograms, mass of sulfur dioxide produced in kilograms. Burning and using the energy to generate electricity and in landfill. Okay, why are life cycle assessments done? So it's really to see what is the environmental impact of a product through its whole life. So to evaluate the environmental impact of a product through its whole life cycle from raw materials to transport, construction, And these are just some of the things. I've not included them all, but and disposal. So essentially, your mobile phone, you look at it and you go, okay, what damage does your mobile phone do to the environment? Well, when you plug it in and you charge it with electricity, some of that electricity might come from the burning of fossil fuels, which releases carbon dioxide and causes global warming. But if we can't just think about that, we have to think about the lithium in the battery that was mined, destroying habitats of animals and plants and removing finite resources which we can't remake, those that lithium metal that's in the battery. We look at the plastics that have been made from crude oil that we'll never get back, and they're in your phone too. And then you've got to think it was transported to the shop in a van, which released carbon dioxide, etc., and all of that kind of stuff. And then when you finally get bored of your phone and you get rid of it, it has to be the battery is toxic, and that will damage the environment if you just chuck it out. And it will take up space in landfill where people could be building houses. So there's all that kind of overall impact of just your phone. Okay, let's move on. Compare two methods for the disposal of biodegradable plastic bags. Use the information from table one. So we want to compare. Now it just says compare. So we literally are just going to say what is the same and what is different. So about each. So um, where am I? Use the information. This is table one. Okay, compare the two methods of disposal. Right. So if we burn and use the energy to generate electricity, we're going to say, okay, burning releases more carbon dioxide. And I'm just going to add an explanation which causes global warming. So that's bad, right? It's kind of bad. We're making, I'm kind of evaluating. I shouldn't really put that because that's an evaluation, but burning releases more carbon dioxide. Um, yeah. Okay. What else can we say? However, however, has less solid residue released. Okay. Which could form particulates. Cool. So, however, less solid residue release, which could form particulates, so it has less solid residue. However, it also burning, whoa, burning produces brunning. What the hell is that? Okay, burning produces less sulfur dioxide, so causes less acid rain than landfill. There you go. So that's just using the information from table one, just straight up that we can get more massive carbon dioxide produced. So that's worse for carbon dioxide, but it's better for solid residue and it's better for acid rain and sulfur dioxide. So let's give ourselves the marks and move on. Bish bash bosh. Now let's go. Okay, we're on question two now, folks. This question is about Earth's atmosphere. Carbon dioxide is a greenhouse gas. What is another greenhouse gas? There's three in GCSE chemistry and combined science for AQA that you need to know about. Three greenhouse gases they like you to know about. So which one of these is another greenhouse gas? Well, the answer is methane. So the three that you need to mainly know about in AQA, unless they tell you otherwise, like in a question, they might tell you, but you do have to know these are the three greenhouse gases in AQA that they want you to know off by heart. Greenhouse gases cause global climate change. Give two effects of global climate change, and it's worth 2 marks. So if the climate changes, what are two things that could happen? And we just need to give any two effects from a big fat list. So we could say increased flooding. Obviously, you're going to get sea levels rising. You could say sea levels rise instead. So I'm just going to put increased flooding, but you could put sea levels rise. We could also get increased droughts, kind of like the total opposite, which is where the ground gets really dry and nothing can grow there. So you can get increased droughts and increased flooding. And there's lots of other things we could put: sea level rising, extinction of animals, a change in the distribution of organisms, plants and animals on the earth. So maybe in the UK we'll have palm trees if it carries on getting warmer. Who knows? But it will, and that will affect the kind of animals that live here as well. All right, let's move on. Bada bing, bada boom. 2.3, 4.1 kilogram of a plastic used to make plastic bottles has a carbon footprint of 6 kg of carbon dioxide. Okay, calculate the carbon footprint of one plastic bottle of a mass of 23.5 grams. It's worth 2 marks. There is no formula for this. This is just a mental maths that they like to give you. Remember, 10% of your chemistry and biology is going to be mental maths and your physics. So here we go. 4.1 kilograms of plastic used to make plastic bottles. Right, I've got two numbers here. They're telling me how much does my plastic bottle, that is the worst. Oh my gosh, I got a D in GCSE art. Let's not draw a bottle. Calculate the carbon footprint of one plastic bottle. Right. What I was trying to say is the masses are different. Why don't you pause the video, have a go? Okay. Um, a 4.1, that is 4,100 gram plastic um, releases 6,000 grams. I know what you're thinking. How's that possible? But because it combine the carbon in the plastic combines with oxygen in the air, so the mass increases. But we've got 4,100 grams of plastic makes 6,000 grams. So what I want to do is find out how many grams of CO2 are there released by each gram of plastic. So what I'm going to do is go 6,000 and I'm going to divide this by 4,100. And this is going to tell me for each gram of plastic bag I burn, this is how much carbon dioxide is released. So let's go 6,000 divided by 4,100. We find we get 1.463, 1.463 grams of CO2, and that's per G. I'm making this long, aren't I? Of plastic. Okay, I think I've longed this one out. I didn't need, they've actually asked me for how many kilograms and I've turned it all into grams. I didn't need to do that. That was super stupid. Anyway, now calculate the carbon footprint of one plastic bottle of mass 23.5. So I just want to times that because what I'm saying is 1 gram of plastic makes 1.463 of carbon dioxide. I've got 23.5 of plastic. So I want to times that by 23.5. I'm sure I could have done that a lot easier. But there we go. Times 23.5. All this converting, and I realize I've got to convert it back. So I'm going to make 34. One bottle has a carbon footprint of 34.939 grams. Now they want the answer in kilograms, so I need to turn that into kilograms. So we're going to divide by 1,000. When you go up the scale from a small unit like grams, you divide. And that can be confusing for people, but think about your height right now. What's your height in centimeters? You might be 165 centimeters. If I said to you, what's your height in meters? Meters is a bigger unit. You have to divide to get to meters. So you do like 165 centimeters divided by 100, you'd be 1.65 meters. And that is a misconception. People get mixed up with that. So when you have a small unit like grams and you want to go bigger, turn it into a big unit like kilograms, you're going to divide. And kilos, we divide by 1,000. So this is going to end up being 0.034. I could leave it at that, but 39 kilograms. And that's going to get me 2 marks. All right, let's move on. Right, 2.4. Give one way that carbon dioxide emissions can be reduced when a plastic bottle is manufactured. So how can we reduce carbon dioxide being released when a plastic bottle is manufactured? So what you can do is instead of disposing, recycle the plastic bottle, or so when they're making it, use recycle. I'm probably better off actually if I read that question properly. I think instead of disposing, recycle the plastic, I think this is the correct answer because actually they're saying when you make it, what should you do? Well, use recycled plastic. So you don't use old plastic bags to make your plastic bottle. So I would go with use recycled plastic rather than they're asking us specifically in the construction of the plastic bottle. Okay, right. Let's move on. Explain how the percentages of nitrogen, oxygen, and carbon dioxide in the Earth's atmosphere today have changed from the early atmosphere. So we want to talk about what was the atmosphere of the Earth like at the start, and then we want to say how it has changed. So it's worth 6 fat marks. grab pen, grab paper, have a go, pause the video. Right, I'm going through the answers. So first up, we can look at nitrogen. And nitrogen, oh my good days, nitrogen was released from volcanoes. So, and also a nitrogen containing compound called ammonia was also released from early volcanoes on the Earth. So we can say nitrogen gas was released into the Earth's early atmosphere. And of course, you know that nitrogen makes up 78% of our atmosphere. So it's basically the most abundant gas in the Earth's atmosphere. Nitrogen gas was released into the Earth's early atmosphere via volcanoes. Also, ammonia that was released via volcanoes was turned into nitrogen by bacteria. So you've got these bacteria that release nitrogen back into the sky, and they're called denitrifying bacteria, and they're going to put nitrogen. But of course, that didn't happen in the first billion years because there wasn't any bacteria. So until life evolved on the Earth, we couldn't have had bacteria changing the ammonia into nitrogen, but we did get a lot of nitrogen gas coming out. So there we go. That's a little explanation of the nitrogen. Now, what else came out? Well, we had water vapor. So in the Earth's early atmosphere, also coming out of volcanoes. Number two is H2O. So water vapor was in the Earth's early, oh my days, early atmosphere. This condensed as the Earth cooled and formed oceans. So we don't really have a lot of water vapor in the air compared to the Earth's early atmosphere because as the Earth got colder, it condensed and cooled and formed oceans. But what we also have coming out of those volcanoes in the Earth's early atmosphere was an incredibly large amount of carbon dioxide. So what's happened to the carbon dioxide? So we want to say the Earth's early atmosphere contained lots of CO2. I mean, I think it contained quite a frightening amount of CO2. Um, and but this then decreased. This decreased to today's levels by, so how did it get down to the levels it is today, which is only 0.04%? It's about 0.04. Yeah, it was 0.03 a couple of hundred years ago, but we've had global warming combustion since the Industrial Revolution. It's sort of creeping back up very slowly. But this decreased to today's levels. And why? Because CO2 dissolved in the oceans. Okay, so carbon dioxide, very soluble, dissolved into the oceans, lots of CO2 dissolved in the oceans, and as they warmed up, the solubility of the oceans increased further, dissolving more CO2, I believe, or maybe not, but whatever. Carbon dioxide dissolved in the oceans. It formed, and now this happened later on, but it formed the shells and skeletons of marine life. Of course, you've got lots of carbon in your skeleton, so it's in all organisms, and it is locked in or formed sedimentary. I don't know why I said locked. It formed sedimentary rocks. It would help if I could spell or type. And then what else? What else? What else happened to the CO2? Locked into rocks, dissolved into the oceans, formed the shells and bones of animals, and then, of course, photosynthesis by green plants and algae about 2 billion years ago. These bad boys was algae-like organisms. It wasn't really algae, it was a cyanobacteria, but never mind. Photosynthesis, they like you to say photosynthesis by green plants and algae, so we'll go with that. Photosynthesis by green plants and algae absorbed CO2 in photosynthesis. So there we go. All of this contributed to the decrease in carbon dioxide in the atmosphere. One gas I haven't talked about, folks, which wasn't around in the Earth's early atmosphere, is oxygen. So we need to talk about oxygen. So I'm going to do that over on the side here. And what we're going to say about oxygen, give me one sec, one sec, one sec. So oxygen was released by plants and algae uh, via photosynthesis. So the Earth's early atmosphere didn't have oxygen. So maybe I'll put that as well as a comparison. Earth's early atmosphere um, did not have oxygen. And we say that it was anoxic. Ooh, without oxygen, that means anoxic. It isn't anoxic anymore. It's about, what, 21% oxygen. And that was released by plants and algae during photosynthesis. So oxygen has increased. So um, I don't know, oxygen is now 21% of atmosphere. I'll tell you what, I think, oh my gosh, check out that spelling. Never mind. Let's move on. This would get you all the 6 bad boy marks. Need to move on, otherwise I'm going to be here forever correcting my crappy typing and stuff. Oh. 3. A student investigated the mass of dissolved solids in 5 centimeter cube samples of water, shows the apparatus. We've got a Bunsen burner. We've got a boiling water. We've got a beaker. We've got a watch glass, and we've got the water sample. Here's the student's results: seawater, river water, rainwater, watch glass. So you can see this is the mass of the water in the watch glass and the dissolved solids. Okay, so that's just the glass. This is the water and the salt all together with the glass, and then the dissolved solids. We can see now they've minus that from that to get these. And then we have the dissolved solids in 1,000 centimeters of water, and we've got X, and it says calculate X in the table. So you can see all we've got to do here, that's 5 centimeters. You just got to find the factor that they've multiplied that by. So you could do 28 divided by 0.14, find the factor and then times that by that. Or you could say, look, this is 5 centimeters and that's 1,000. So really to find the multiplying factor, you could just, oh my gosh, I'm in white, so it's not going to show up. Okay, there we go. We've got 1,000, and you're just going to divide it by, oh, that's in white too. This is a bit long. Divide it by 5. What is 1,000 divided by 5? That should be nice and easy, right? It should be 200. Yeah, easy peasy. Even I can do that. 200. So essentially, and then you can just check, is that correct? What you want to do is check, do 0.14. So you use a bit of maths common sense, times 200, you get 28. So it's correct. So we're then going to do 0.08. We're going to times 200, and we're going to get the correct answer. Now, there are more, yeah, I explained there's more than one way to do this, but there we go. The answer is 16, folks. 16. So X would be 16. Let's give ourselves a tick. Okay, bit of mental maths. Like I said, they love a bit of mental maths. So it's not that you just got to think on your feet with those ones. Okay, 5 centimeters is a small volume of water for each experiment. Give one advantage and one disadvantage of using a larger volume of water. So obviously, using a larger volume of water, it's going to take longer to find out how much salt is in there, because it's going to take longer. You're going to have to evaporate that water to just leave behind the solid. So that's going to take longer. However, the advantage to using a larger volume of water is it should be more accurate. There should be a smaller percentage error. I'm going to put those in there. It will be more accurate, less percentage error. Think about it. If you've got like, yeah, there's going to be less error. Like, right? Let's say your equipment or whatever, your mass, your scale for weighing things, weighing the grams is 0.01 out. Well, if you make a mistake of 0.01 with 5 grams, that's a certain percentage of error, right? 0.01 over 5 times 100, and you'll work out the percentage error. But let's say you're still got the same scale, so it always makes a mistake of 0.01. But if you're now using more water, so there's going to be 20 grams of salt, your percentage error is now 0.01 divided by 20 times 100, and it's a lot smaller. So you're going to have a smaller percentage error. It's going to be more accurate to use larger volumes. Now, the disadvantage is it will take longer to evaporate the water. So the experiment is going to take a lot longer. Now, 3.3, potable water is not pure water. Describe the difference between potable and pure water. So what's the definition of potable? So potable water is water that is safe to drink. However, it is a mixture. It contains other chemicals, not chemically, yeah, it just contains other chemicals. Pure water only contains one substance, I've over-explained this, the compound H2O. So pure water just has H2O molecules. As you know, when you drink water, look on the back of your water bottle, it will tell you there's potassium, there's lithium, there's calcium, there's all sorts of ions, maybe not lithium, but there's all sorts of ions dissolved in your water. Okay, so one's a mixture, one is just made of one substance. Let's move on. 3.4. Potable water is obtained from both groundwater and from seawater. Describe how groundwater and seawater are treated to produce potable water. So it's 3 marks and it's just described. We don't need to explain. So we just need to say what happens. So groundwater, how is it treated to produce potable water? Well, groundwater is essentially filtered. Okay, so you're going to remove twigs and stuff like that by basically sieving out any twigs and stone and grit. You filter it with sand and stones in a sand bed. Then it is sterilized using like chlorine or ozone. So you could, those are just 2 suggestions. You can use other things to sterilize it. Seawater treated, seawater undergoes distillation to remove the water from the salt. It is then sterilized. I'm just going to put, yeah, sterilized. I don't need to repeat what we use for sterilization. There we go. So really it's the fact that groundwater's filtered and then sterilized. Seawater does distillation, then sterilized. Cool. Don't forget, if I forget to say, pause the video, have a go at the question, and then unpause and watch my explanation. 3.5, the percentage by mass of dissolved solids in a 6.50 gram sample is 2.2%. Calculate the mass of the dissolved solids. So the percentage by mass of dissolved solids in a 6.5 gram sample is 2.2. So you basically, what is 2.2% of 6.5? So that's kind of easy, isn't it? We're just going to go 2.2 divided by 100 times 6.50 and grams. And what's that going to give us? Well, something like 0.12 or something like that. I've got no idea. Let's actually find out. Let's do the actual calculation, Tom. 2.2 divided by 100 equals that times 6.5. Nope, it's 0.143. Okay, 0.143. I was like 0.12. That wasn't that close. Okay, 2 marks. Don't know why that's 2 marks. Dead easy, piddly peasy. Right, we're going on to question 4. Fertilizers are formulations. What is a formulation? So if you think of crude oil, which is a mixture of different hydrocarbons, we did that in the first question in this paper. Crude oil is not a formulation because it's a natural mixture that you find out there and you haven't really planned what different things are going to go in there. Whereas with a formulation, it is a mixture which contains components or like the substances in the mixture are in very specific exact amounts. So a formulation is a mixture where the components are in specific amounts. I don't need to say specific and exact. So what I mean by that is if you're making a toothpaste, you might need a certain amount of calcium carbonate, a certain amount of fluoride, a certain amount of water, and you have to mix them in that exact amount. So that is a formulation. Right, let's move on. 4.2, a bag of fertilizer contains 14.52 kilograms of ammonium nitrate, NH4NO3. The relative mass, MR, NH4NO3 is 80. Thanks. Done that for us, haven't they? Calculate the number of moles of ammonium nitrate in the bag of fertilizer, give your answer to 2 sig fig, and it's 4 marks. What a lovely, easy peasy question. Let's go, peoples. Pause the video, have a go. All right, I'm going to go through it. So first of all, we have, they've given us mass. Personally, I like to, in chemistry, kilograms, you're going to change to grams, especially if you're trying to look up moles, you're going to need grams. So you're going to times that by 1,000, and we're going to have 1,452. Hold on, Tom. That's 14,000. What am I on about? 14.52 times 1,000. Yeah, 14,520 grams. Lovely. Now, the fact that we've got mass should get your brain ticking if you're a chemist. And then look, these bad boys give us MR. That means we know we are going to be doing this equation, and it is mass over MR times moles. You need to know that off by heart. If you don't know it, get it on a revision card. It's the most important equation in chemistry. So you're going to do mass over MR. We know the MR is 80. So that's all we've got to do, folks. You get 1 mark for converting the mass from kilograms to grams, like that. Then divide it by the MR of 80. So mass over grams over MR. And that is going to give us, divided by 80, that's going to give us 181.5 moles. And I use N for number of moles. So we got a mark for timesing that by 1,000. We got a mark for doing the right equation. We got a mark for working out the moles. We now need to do it to 2 significant figures. So you were only allowed 2 numbers other than zeros. So we basically have to decide, are we going to do 180 or 190? What would you go with, 180 or 190? Well, it's obviously closer to 180. So we are going to do 180 moles. And there we go. When it's 2 sig fig, you can only use 2 numbers. You don't have to include zeros in those. You only use 2 numbers. Obviously, we still need to put the 0, but 180, it's closer to than 190. So instead of 190, we go 180. And there we go. Let's move on. Okay, the fertilizer also contains potassium chloride. Explain why potassium chloride has a high melting point. So this is a 4 marker. Why don't you pause the video now, grab your pen, grab your paper, have a go. All right, I'm going to go through it. First thing to do with these questions, this is about bonding and structure. And the first thing to do is spot that potassium is a metal and the chloride is not a nion metal, it's a no, not an NP. It's a non-metal. Okay, so we've got a metal and a non-metal. That will get us no marks, but it does help us if you know what a metal and a non-metal form when they come together. They form an ionic compound, not a metallic, not a covalent, but ionic compound. And why do they have high melting points? In fact, there's one key word here. Every time there's a high melting point, anytime you see that, that always, 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 the answer to that is the word giant. Better if you say giant structure. So, but if you said giant ionic, that's 2 bad man marks. So let's put it down right. Potassium chloride has a giant ionic structure. And look, we've just got 2 marks straight off the bat. Now, I'm going to explain what an ionic bond is, but sometimes you don't need to. They're a bit like 50-50 on this, but if you want all 4 marks, you can do. So it has lots of strong, and I'm going to put ionic bonds. Sometimes they'll just allow you to put that. Now, notice I've put lots of and strong. So I've put the word lots of and strong. Now, sometimes I'm going to put in brackets. You need to explain what an ionic bond is sometimes. And it's best to if you can remember. So what is an ionic bond? So when I said lots of strong ionic bonds, instead of ionic bonds, I'm going to say lots of strong electrostatic forces of attraction between oppositely charged ions. God, that's not gone too well. Don't look at the typing in there. That is foul. And I'm not talking about chicken. Okay, lots of strong electrostatic forces of attraction between oppositely charged ions. Now, the big thing, oopsie, the big thing here is sometimes they'll just let you say strong ionic bonds. Sometimes you need to say lots of strong electrostatic forces of attraction between oppositely charged ions. If it was covalent bonds, we'd say lots of strong electrostatic forces of attraction between shared pairs of electrons and positive nuclei. If it was metallic bonds, which is the third type, then you'd say lots of strong electrostatic forces of attraction. So that bit's always the same, but this time you'd say between positive metal ions and delocalized electrons. So those are the three definitions. If you don't know them for the three different bonds, the complex definitions, you should put them on a revision card. Anywho, potassium chloride is a giant ionic structure, lots of strong ionic bonds, and I'm going to put here they take lots of heat energy to break. So you've got all these strong bonds, they require lots of heat energy to break, and that's why they have a high melting point. Anytime you see the word high melting point, you have to have a giant structure because that means you have lots of strong bonds. So if you don't have a giant structure, you can't have lots of strong bonds, you can't have a high melting point. Anywho, let's move on because I'm waffling. Okay, question 5. A student investigated the effect of the size of marble chips on the rate of reaction between marble chips and hydrochloric acid. This is the method used. Add 10 grams of marble chips onto the flask, into the flask even. Add 50 centimeter cubed of hydrochloric acid, connect the gas syringe and start a timer. Boop, boop. Record the volume of gas produced every 10 seconds. Oh, have a look. Figure 4 shows the apparatus. We've got hydrochloric acid, we've got marble chips. There's some sort of bubbles coming off there. Complete the equation for the reaction. So you've got to know how to do these equations. Calcium carbonate plus acid. So calcium carbonate's a base, but it does contain, it's a carbonate base, metal carbonate, plus acid, and you have to know the standard of what they produce. And they're going to produce a salt, water, and carbon dioxide. Why don't you pause the video, have a go? All right, I'm going to go through what they're going to make. So calcium carbonate and hydrochloric acid, they're going to make a salt. And when you name the salt gets the metal from the base. So whether it was calcium oxide, calcium hydroxide, or calcium carbonate, or if it was just calcium metal alone, you're going to take the word calcium, the symbol for calcium, and that is the first part of the salt. The second part of the salt always comes from the acid. Acids always have an H in front, so it's CaCl. Now, is it CaCl2? Is it CaCl3? Or is it just CaCl? Well, in order to know that, I have to look up what group they're in. And calcium's in group 2 of the periodic table, which means it has a +2 charge. Chlorine is in group 7 of the periodic table, and chlorine always forms a -1 ion. So I'm going to need two -1s to equal +2. So it's going to be CaCl2. And that is the calcium chloride. And then I just need to do water, always comes off in these neutralization reactions, and carbon dioxide. And now I just need to make sure it is balanced. One calcium, one calcium. I'm going to need a 2 here straight away because I need 2 chlorines, and that takes care of the 2 H's for the water. There's the 3 O's over there. There's 1 C. That is all balanced. I just need a 2 there and then all of that there, and that is balanced up. Awesome. Bish bash. Okay, we've got a graph. Figure 5 shows the student's results. Here's the volume of gas produced, and that gas is obviously carbon dioxide. Now, this says describe the trend shown in figure 5. Use values, 3 marks. Okay, so they're normally 2 marks when you describe the trend, and all we need to do here, describe, no explanation. You don't need to talk about chemicals reacting, anything like that. You just need to describe the line, so, and what's going on in terms of what you can see. But look at this graph. We can see 3 parts to it. So we just need to describe the trend and use numbers to get all the marks. So there's kind of 3 parts. So what I want to say is between 0 and 10, so that's using values, or I can just say, yeah, okay. Between 0 and 10 seconds, the volume of gas increases. Okay, and that's all you need to say for that mark. You just need to use the numbers to say stuff. And then I can say between 20 and 30, it doesn't increase as much. So between 20 and 30 seconds, it is still increasing, but not as fast or not as much, right? It's increasing, but more slowly. Look, it's bending. So that is going to get you 2 marks. We've used the numbers. Now, I could have said between 10 and 30 or whatever. Now, between 30 and 40, it's not increasing at all. No more gas is coming off. And that's all I have to say. So between 30 and 40, no gas is coming off. It is level, plateau, level, whatever. And that's all you've got to say. Say what you see. There's no science needed here. Just describe what you see. Okay, 5.3. Describe how you would use figure 5 to find the rate of reaction at 15 seconds. You don't need to do a calculation. Quite often you will have to do this, so I'll show you what you do anyway. It's worth 2 marks. So why don't you pause the video? How would I find the rate of reaction here? Look, there's 15. That's where 15 would be, bang in the middle of 10 and 20. So how would we find the rate of reaction there? We can't just use the normal gradient because it's a curve. So what you need to do, hopefully you know what this is. Oh my days, this is going to be disgusting. Yeah, you've got to do this line like that. To be honest, the line should be even on both sides by the eye. It's not, is it? It's quite big, the space there between the curve and my line, and it's not very big over here. So this is absolutely pants. And what I need to do is redo that. And I'm going to use a different color as well, just so that we can actually see the difference. So let's try that. I think that's flopped even harder, but you get the idea. So I'm going to do this, and then what you're going to do, you're just going to pick two. You're going to make a little triangle. You can make a triangle anywhere like that. It doesn't matter. And then you'd read off these points, and essentially you do the change in Y. So you'd read off the point there and the point there and work out the change in Y. And then you would divide that by X, and you do Y over X, and that would give you the gradient. And that's called, this line here is called a tangent. So you use a tangent to work out the change in Y over X, and that would give you the answer. Okay, we just need to put that down. So what we're going to do is describe how to do it without doing a calculation. So at 15 seconds, draw a tangent to the curve, then work out the change in Y divided by the change in X. And that is basically explaining how you work out the reaction rate when you're dealing with a curve. Give the units for this rate of reaction. So we need to go back up and look at the graph and see what the units are on your graph. That's all you've got to do. Dead easy. Right, look, check this here. Centimeter cubed. And remember, I said we're doing Y over X. So you're just going to go centimeter cubed, draw a divide line just like that, Y over X, and then seconds. So centimeter cubed seconds. Now, if you were really fancy and you were studying A level, you'd write seconds to the -1. You do like that. We don't need to do that though. So we're just going to put centimeter cubed per second. And so let's scroll down. And if I want to write that in, it would be like that, centimeter cubed per second, and that would get us a mark. Now, table 3 shows the results of the investigation, the relative size of the marble chip, small, medium, and large, volume of gas produced in centimeter cubed after given time in seconds. Okay, so great. Give one conclusion about how the size of marble chips affects the rate of reaction. Again, this is like describe. You don't need to use any science. Just basically what happens as the chips get larger. Let's have a look. So as chip size increases, I haven't actually had a look yet, what happens to the volume of gas produced? So as the chips get larger, look, there's less gas coming off. So it comes off more slowly. Actually, the total amount of gas after 60 seconds is equal. So I don't want to say they give off less gas. I'm going to say they release gas more slowly. So as the chip size increases, the gas is released. The gas is produced more slowly. Basically, it's a slower rate of reaction, okay? So you've got a slower reaction. I might just add that as well. Slower rate of reaction. So you're getting less centimeter cubed per second. Just in case, put the extra. Suggest why all three sizes of marble chips produce a maximum volume of 60 centimeters of gas. So what's the suggestion? I might have a small chips, I might have some medium chips and some large chips. Why did they only give out the same amount of gas? So the reality is here that all the acid is used up, or we have the same mass of chips. What I need to do is just go and check what if the question said anything that's specific up here to do with it. 10 grams of marble chips were used. Yeah, we had the same mass of chips and 50 centimeters of acid. I don't know which one got used up first, the acid or the chips, but essentially, whoa, what was that? Oh yeah, there we go. All right, here we go. Right, so they used the same mass of chips, so that was the maximum product produced. So it looks like yeah, that's the maximum they could produce. Same mass. You've got the same amount of reactants, essentially. Exactly the same amount. It's just happening quicker with one and slower with the other. Figure 6 shows 8 small cubes, each 1 centimeter, 1 centimeter, 1 centimeter, and one large cube, 222. There's the 222. There's the calculate the surface area of the large cube. So, okay, calculate the surface area of the large cube. That's kind of easy, isn't it? So the volume of the large cube is 8. What is the surface area? See, they've got the surface area. That one is 8 to 48. What's our one? Well, it said it was 2. So we're going to go 2 times 2, and everyone can do 2 times 2. That gives us 4 centimeter. So we're going to go 2 times 2 equals 4 centimeter square. But of course, there are 6 sides. So I need to times 6. We're going to get 24 centimeter cubed. And that's going to get you 2 marks. Bish bash. Now, we can use this information. Check this out. If you were to look at this, this is the surface area is 3 times bigger than the volume in that cube. But look how many times bigger it is here. What is that? That's 6 times bigger. So this has a surface area to volume ratio of 6 to 1. And this is only 3 to 1. So the smaller the cubes, the bigger your surface area. Let's sink down and do the next question. So 5.8, explain why the size of the marble chips affects the rate of reaction. Give your answer in terms of collision theory. So what we want to say is larger marble chips have a smaller surface area to volume ratio. I saw it there. It was only 3 to 1 with the 2 centimeter cube. The small 1 centimeter cubes had a 6 to 1. So the large marble chips have a smaller surface area to volume ratio. This means there are less frequent collisions between there's less particles available to react essentially between the reactants. So you get less successful collisions, less particles available to react. Yeah, whatever. Bish bash bosh. Okay, 5.9. The student repeated the investigation with marble chips using hydrochloric acid with a lower concentration, shows the volume of gas produced during the first 40 seconds. So look, they used a lower one. Explain why the results for the lower concentration are different from the results for the higher concentration. So there's 2 ways it's different. So you'll notice it's coming off more slowly. And also the final resting place when the reaction finishes, it gives off a smaller volume of gas. And we're going to put an explanation for that. Why don't you pause the video and have a go? There's 2 points to consider here. Okay. First, it reacts more slowly as there are less reactant particles. So fewer collisions. Now I'm going to put per second. So the frequency of collisions is less, but because I started typing it like that, I've just gone with, it means the same thing. Frequency is per second. So basically I'm saying there's less collisions per second because there's less particles to collect, to react. So first it reacts more slowly as there are less reactant particles, so fewer collisions per second. And then what we want to say is the total volume of gas is less as there are fewer, ooh, fewer reactants. Ah! So I've got fat fingers, so fewer products, unfortunately. If I could get my fingers on a diet, I would. I might get liposuction on the old fingers. Right, let's go. Um, we're on the last question. Bleach is a solution of sodium hypochlorate, NaClO. Chlorine gas is produced when bleach reacts with hydrochloric acid. There's NaClO plus 2 hydrochloric acid goes to reversible symbol goes to NaCl plus water plus Cl2, and you've got the state symbols aqueous, 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 liquid, gas. Give the test and the result for chlorine gas. So you have to know a load of gases. Oh, green, chlorine's green. You have to know a load of gases and their tests. So what is the test for chlorine gas? It bleaches, um, damp, or it bleach. Oh, I can just put it bleaches litmus paper. Yeah, bleaches damp. Oh, maybe we'll put damp. Come on, bleaches damp litmus paper. Okay, actually, it's 2 marks. So I'm going to say it turns litmus paper red, then white as it bleaches. And I don't know how to spell bleaches. I think that's it. The paper. Okay, so first of all, the acid is an acid. So acids turn litmus paper red, and then it's going to bleach it white. Okay, and that's going to get us 2 marks. I thought it was a 1 marker, but it turned out to be 2. So red, then white. Figure 8 shows a sealed flask of sodium hypochlorite and hydrochloric acid at equilibrium. Sodium hypochlorite and hydrochloric acid. Explain why equilibrium is reached in this reaction. Have a look. What have they got? In order to have equilibrium, there's some factors you need. And let's go up here. Can you spot why this is a reaction that can reach equilibrium? You could pause the video and have a go, but hopefully you've spotted there's a reversible symbol. Only reversible reactions can reach equilibrium, and they have to be in a closed system. And what we mean by a closed system is they need to have a lid on. Otherwise, they can never reach equilibrium because things can escape. Okay, so what we're going to do here is it is a closed system as the bung is in flask. I don't think we need to explain that, but it's just a closed system. And it is a reversible reaction. And there we go. That's going to be our 2 marks. Right, 6.3, the stopper in figure 8 is removed and hydrochloric acid is added. The stopper is replaced. Explain what happens to equilibrium. 4 marks. Why? Let's go. Right. So what they're saying is they've added hydrochloric acid. Now, there's a dude called Le Chatelier, and I never know if he's called Le Chatelier or if he's just Le Chatelier, basically, because his name's spelt like Chatelier, Chatlier, something like that. Anyway, he came along and he made a principle. He basically said that whatever you do to this reaction, it will shift its equilibrium in the reverse direction. So if I add more water, the reaction will say, what are you doing? And it will start to get rid of the water by forcing the reaction this way. The equilibrium position will shift to the left. If I add more sodium chlorate, more bleach, the reaction will go, what are you doing? And it will try to get rid of the bleach by reacting it with hydrochloric acid to make more of this. If I add more chlorine, the reaction will say, oi, don't do that. And it will start reacting the chlorine with the water and this to make these. So they've said acid was added. Explain what is going to happen to the equilibrium. The equilibrium position will shift to the right in order to oppose the change. So it's going to shift to the right to remove the hydrochloric acid and oppose the change. Let's go and put that in the answer area. Okay, the stopper in figure 8 is removed, hydrochloric acid is added, the stopper is replaced. Explain what happens to the equilibrium. So we're going to say the equilibrium position shifts to the right hand side in order to oppose the change, which is an increase in the concentration of HCl. So it shifts to the right to reduce the HCl. It was a bit long, that, wasn't it? So essentially, the HCl will decrease the concentration. So first of all, it goes up, then it shifts to the right, decreasing the HCl concentration to reach a new equilibrium that is positioned more to the right. And I could say we would increase the yield. You're going to get more of the things on the right, but basically increases the yield of products on the right hand side. Just in case, I can't remember the names of the product, what was on the right, chlorine gas. So we get more, I could just name something, more chlorine gas is produced. You're going to get more chlorine gas, basically. There we go. That's 4 fat marks. All right, let's move on. We're nearly done with this test. Oh yeah, baby, 2 more bits. Chlorine gas is also produced when hydrogen chloride decomposes. Here's hydrogen chloride decomposing in a reversible reaction to form hydrogen and chlorine. The forward reaction is endothermic. Predict the effect of increasing the temperature on the amount of chlorine gas produced at equilibrium. Explain your answer using Le Chatelier's principle. Okay, what you need to do with these is when you see that the reaction is endothermic, whenever they say a reaction is endothermic, or they're talking about this, the right-hand side. And what I like to do is I think of endothermic as cold. Now, you mustn't use the words hot and cold in your answer, you won't get the marks. But in order to visualize it or kind of in your head, this really helps. So if it's endothermic this way, it's exo that way. So that means that the cold side is endothermic. The right-hand side is always the name of the reaction. So this is endothermic, and this is exothermic. Sometimes it's the other way around, exothermic on the right, endothermic there. But we're told the forwards reaction is endothermic. So it's cold on that side. Remember Le Chatelier, he said, whatever you do, it will do the opposite. So if you increase the temperature, what did Le Chatelier say? He said it's going to do the opposite. So we're going to make it hot. It's going to go, whoa, I'm already, whoa, I need to cool it down, baby. So it's going to move to the right in order to cool it down. So whatever you do, the reaction opposes your change. So what we want to say is the reaction will shift, and this is the technical language you need, the equilibrium position to the right to oppose the change in temperature because the right hand side is endothermic. It's the cold side. Now, really what happens, the right hand side is absorbing energy. So when you increase the temperature, the right hand side is endothermic, so it will absorb that energy, which will decrease the atmospheric temperature. Okay, or of the environment. Explain the effect of increasing pressure. We've got the same thing going on. Now, what you do when you're looking at pressure, let me get off my red. All right, when you're looking at pressure, you're looking at the number of gas molecules. So I've kind of moved that in the way so you can't even see the amount of gas molecules. So let's have a look. How many gas molecules are over here? Well, let me draw it out for you. On the left-hand side, there is 2 HCl's, right? 2 of them. On the right-hand side, I've got 1 H2. And I know you might say, but hasn't it got a little 2? Nothing to do with it, because what H2 actually means, H2 is just one molecule. It just means you've got HH. They're bonded like that. So it's just one molecule. Cl2 is just one molecule. Again, I could just write Cl2, or I could do it like that just to show you. It's just one molecule. So actually, I could put a bond in here if that helps. Actually, I've got the same amount of gas molecules on each side, and that means the pressure is even. So increasing the pressure will have no effect on equilibrium because you have the same amount of gas molecules on either side. Now, if I had 2 here, let's say that didn't exist, and 1 there, and you increase the pressure, it would shift this way to where there's less gas to try and reduce the pressure because it always does the opposite. So when you increase the pressure, it always shifts to the side with the least gas molecules. But here, the gas is even. So we want to say there is the same amount of gas molecules. You can use the word moles on each side. So changing pressure doesn't matter whether it's up or down. They've said up here, but so changing pressure has no effect on the equilibrium position. Now, this is really important. You might be like, oh, sir, I wrote in my exam, changing the pressure has no effect on the reaction. Why did my teacher not give me the mark? You have to use the technical language because changing the pressure will have an effect on the reaction in something called reaction rates, which is in paper, well, yeah, paper two like this. So when you increase the pressure, you always increase the speed of the reaction because the particles are going to be smashing together more quickly, more frequent collisions. But specifically, it has no effect on equilibrium when the pressure, because the pressure is even on both sides. So equilibrium and reaction rate are two different things. So watch out for that. Okay, coolio. That's the end of the test. Don't forget sharing, caring, hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on the next video. I've got tons of these. Make sure you work through them. Good luck with your exams.
You're still here? It's over.